final thought, and then we'll be around for some questions. So let's finish up talking about seismic displacement of retaining structures. These are structures, a small sample of structures that were strongly shaken by the magnitude 8.8 Maui earthquake. None of them had problems. Most of them were not designed for seismic forces. We saw the same thing in Turkey for not well-built basement walls. None of them failed. Looking at the 1971 San Fernando earthquake in the near-fault region, Clough and Ferrazzi saw that you had to get to accelerations greater than 0.45 G before they started to see these walls, which were not designed for seismic, fail. So properly designed and built retaining structures have performed well in numerous earthquakes, and they're documented in a lot of the GEAR reports. When you have problems with retaining walls, it's typically a poorly designed wall, or a poorly built wall, or a wall that has been built on top of soil that liquefies or loses strength as a result of earthquake shaking. So therefore, well-designed walls have been proven to withstand earthquake shaking if the PGA is less than or equal to 0.3 G. The static factors of safety of these walls are well above 1.5, so low levels of shaking are not going to cause instability. I'm making your life easy right now. You do not have to do a seismic design of a wall that has a PGA less than or equal to 0.3 G. That's only true if there's no materials that will lose strength as a result of earthquake shaking. If the peak ground acceleration is greater than 0.3 G, and the material behind the structure or below the structure will not liquefy, then conventionally you use pseudostatic methods, such as what Professor Kramer mentioned, Monrovia-Okabe, or the Seed and Whitman simplification, or you use the seismic displacement method. Whitman suggested this, and I built on it, or you do the finite difference, finite element analysis. The pseudostatic method, the equation KAE, which is the dynamic active earth pressure coefficient, is largely a function of the seismic coefficient, the slope, and these other parameters are not as important. So I typically set KV equal to 0, and I focus on KH and beta. For the common case where the backfill is level, Seed and Whitman said if beta is 0, you can approximate KAE not with a long, complicated equation, but by saying it's Ka, where Ka is the active earth pressure resultant by Rankine earth pressure, and then you add on the incremental thrust from the earthquake, which is approximated by Seed and Whitman as being 3/4 of KH. I do believe you should include half of PGA on the wall. Often it's not a big deal, but when it is, it's not a difficult calculation to use the seismic coefficient of 0.5 on a concrete wall. For a level backfill case, KAE depends on the seismic coefficient. So what seismic coefficient do you use? If you go into the literature, you'll see magical rules like 1/3 of the PGA to the 1/3 power, or KH equal to the PGA, or half the PGA, or 2/3 the PGA. There's various values out there. Shouldn't, you've heard this before, shouldn't the seismic coefficient depend on the level of shaking and how the earth structure is responding to the ground shaking? Shouldn't it also depend on the criticality of the structure and what you believe is acceptable level of performance? shouldn't it depend, at least indirectly, on the amount of allowable displacement? So how do you select that K? You admit that there's the equivalent acceleration concept. You know K max is a function of this maximum equivalent acceleration. In this case, it's a little bit simpler because we kind of know what the geometry of the failure plane is. So for this case, we can just use the period of the earth mass behind the wall can be approximated 90% of the time as just being 3.2 times the height of the wall divided by the average shear wave velocity of the material. Just a rough idea of that. Then K max will be a function of the spectral acceleration at the degraded period of the sliding mass. It will not be peak ground acceleration unless it's a very small wall where you say, okay, it's essentially rigid. And the design KH will depend on this spectral acceleration at 1.3 TS and the allowable displacement, where the design seismic coefficient is a percentage of K max. And that percentage, whether it's 90%, 2/3, 1/2, 1/3, is a function of displacement. The lower the percentage, the more displacement you're accepting. Jorge did 3 million analyses. He did it of a block, but now we're using a block representing the earth behind the wall. He got results in terms of predicting permanent wall displacement versus the spectral acceleration at the degraded period of the system. Obviously, the higher the KY is, the less displacement. The greater the acceleration is, the more displacement. But let's simplify this, because you're not typically going to do a dynamic analysis of a wall, so let's pick the seismic coefficient just like we did before. Let's pick a seismic coefficient that depends on this acceleration and what you consider to be permanent, the allowable level of displacement. If you can only accept 5 centimeters, it could be a high seismic coefficient, but if you can let the wall move out 15 centimeters, then you could use a lower seismic coefficient for this value. So this is the procedure using the updated analysis by Bray and Macedo. It's the same thing we talked about. You have the difficulty of picking the allowable displacement. You have to characterize the earthquake shaking and the probability of what you want to accept. You calculate the seismic displacement as a function of these input parameters using the spreadsheet. If you perform a pseudostatic Mononobe-Okabe type of analysis with K equal to this value, and you calculate a factor of safety for sliding greater than 1, then if you had done a displacement analysis, it would have been less than what you judged to be the allowable level of displacement. How can we simplify this for building codes? This is what was used in Canada. Working with this data, they wanted a simpler version. So we said, there's only 2 levels of displacement we care about. We care about things that are sensitive, we'll say 5 centimeters. Things that can take more deformation, we'll say 15 centimeters. So you select one or the other, 5 or 15 centimeters. You estimate the period of the wall of the sliding mass as being 3.2 H over Bs. And then you round it off to either 0.1 or 0.3. Most building codes will allow you to estimate the spectral acceleration at some return period at 0.1 or 0.3. Of course, you need the magnitude because that's duration. Then you do a pseudostatic analysis with a K calculated with these equations below. So for example, if your system was in the 0.05 to 0.2 range of period, and you could accept 15 centimeters of displacement, you would put in your magnitude times the spectral acceleration at a period of 0.1 second, and that would be your K. Don't use this for accelerations greater than 2g, because this is a simplification, and if you've got really high accelerations, you shouldn't be using a simplification. If the allowable displacement is only 5 centimeters, then you're going to see that this is a greater number, and so you're going to design for a higher seismic coefficient to make sure the factor of safety is greater than 1. If you have a bigger wall that's in the 0.2 to maybe 0.4 second range, maybe you could go out to 0.5, but I wouldn't go beyond 0.5. You round it off to a period of 0.3, and you use these equations at 15 centimeters and 5 centimeters. So we're always saying, at a minimum, a rational basis for picking seismic coefficient is not just the seismic demand, which is represented by spectral acceleration at 2 different periods and magnitude. It's a function of what you and the owner have decided is the allowable level of displacement. Now, these are yielding walls. If you have a non-yielding wall, you should still include the inertia effect on the wall itself. But now the pressure on the wall are going to be a little greater. The Wood solution and earlier approximations were overly conservative. So what's typically done now for the level backfill case is something like the Seaton-Whitman simplification, where you're saying, okay, the dynamic total thrust is the at-rest static earth pressure plus the dynamic thrust. And so we know this, it's just 0.5 times K naught times the total unit weight, H squared, where for most sandy soils, K naught is 0.4 to 0.45, and you have a triangular pressure distribution. But then you add on the dynamic increment to get your total dynamic thrust on the wall, and that is delta K naught OE times the unit weight times H squared, where this is estimated as being 3/4 of the PGA. The pressure distribution is uniform here, so the thrust will be halfway up the wall. That's the recommendations of Sitar et al. 2012. An alternative approach, which was used on the BART project, an important project in the Bay Area of San Francisco, was using whatever you calculate as not the total, but the increment of Motonobe Akabe times 1.5, and you place that 0.6 H up, so a little bit higher up on the wall, so it actually will calculate a slightly higher moment. Those are the 2 ways I would go after this problem. Thank you for the sponsors. But thank you most importantly for the course coordinators. This has been a well-run course. We've really enjoyed the interaction. It would not have been possible without the great support, the leadership of Edgar and Guillermo, and then especially we've interacted a lot with Monica and Felipe over the last couple of days, and we know they've put a lot of hours into this. Someone has to buy them a drink tonight. We have to run off to the airport, but one of you has to, all of you buy them 1 drink each, and then they'll be very happy. Thank you. We went over the last couple of things relatively quickly, so if you have questions, we can answer those, and if people have to leave, we'll stay up here for a while and answer questions as well. But if we have some overarching large questions or big questions, we can answer them now.
Tengo una duda respecto para determinar, digamos, análisis hidrostáticos para mirar la estabilidad y determinar los valores de cada excedencia. Digamos, en la norma, por ejemplo, se habla que para los análisis hidrostáticos se deben utilizar parámetros de resistencia efectivos. Sin embargo, en una de las diapositivas, el profesor decía que se hizo el análisis con parámetros de resistencia no drenados por el tema de que era una sacudida, digamos, súbita, ¿me entiendes? Entonces, me genera eso confusión. ¿Qué es lo correcto? Sobre todo cuando tenemos materiales finos, arcillosos.
For fine-grained materials, and for example, a saturated clay, the response of the soil will be best represented by a total stress analysis of the saturated clay using the undrained shear strength, modified for rate effects and cyclic degradation. That's the correct way. So if you had a fill on top of a soft clay and you had a slope stability issue, the strength of that clay would be best evaluated in terms of the field-based shear test to get the peak static strength that you could adjust for rate effects and cyclic degradation, or using a cone correlation, or using some type of sampling and testing. If the soil, if you're analyzing a landslide that has moved, and you believe that the soil is down to residual strength, and it is gotten down to that residual strength, then you could use a drain friction angle to represent that residual strength for a earthquake-induced deformation problem of an existing landslide. But in the end, the general answer is you have to use the strength that best represents the loading path and the time of loading. And for most cases in earthquake engineering, that's going to be the undrained shear strength, except if you have incredibly good drainage.
You use one undrained friction angle. You use an undrained friction angle. Here, when you say undrained, it's P0.
If it is a saturated material,
you have a PU21 undrained friction angle.
If it is a saturated material, then it should be VU equal to 0. But if it's a partially saturated material, that dam, that area that the slide was going through was partially saturated, then the way the consultant characterized the material was a total stress characterization. And so they ended up with a total stress C and a total stress V.
No, here usually not V is always 0.
If it's a saturated material, VU has to be equal to 0.
No, but it doesn't matter. Here is only V0. Another question. You say no wall has any problem. Just one comment. Wouldn't it be that they use all mononomial coverage like everybody uses and it's conservative?
Now, most of the walls that we investigated, when we talked to designers, they did not consider active earth pressure thrust on basement walls and a lot of the wall systems. So, like Kobe area, there was not a design for seismic consideration. And Düzce in the Turkey earthquake in 1999, they did not design the basement walls, they did not design the retaining walls for seismic consideration. So what we have found is earth pressures on walls are something to think about, but as Professor Kramer mentioned, it really is, in many cases, the wall and the soil are moving together. So it really is, if you have a large or tall wall with a softer soil, I can see incompatibility in loading. But I don't see that for a short basement or a short wall and a stiff soil. I think they shape together.
two questions. Professor comment, which is the reference, and if that expression includes statural and lateral pressure effects. Expression. Okay. The expression includes lateral pressure, static lateral pressure, and which is the reference.
I'm not understanding what you're.
Which is the case expression for the slide about more realistic view.
The Brandenburg, Lilakis, and Stewart equations, does that loading you're taking include static as well as dynamic?
No, that's just the dynamic component of loading. That have to be added to the static. So they're just considering the dynamic response to that problem, and only the kinematic part of it. The walls are essentially assumed to be massless in those conditions.
Which is the expression, the reference.
The reference?
Yes.
There's papers by Brandenburg, Stewart, and Milonakis in the ASC Journal of Geotechnical and Geoenvironmental Engineering. It's about a year old or so, a couple of years old. I think they've published some more work on that recently.
And one question for the
que no tenía deberes.
SK, what is the damping for your expression? Can you say?
Okay, so for just like when you do a lateral pushover analysis of a building, the building is not going to have exactly 5% damping. We're just using that as a index. I'm doing the same thing. I'm using the 5% damped spectral acceleration of a single degree of freedom system to that ground motion as an index of the dynamic loading. Okay? Remember, we use 5% damping as a filter so that we can see the frequency content of a ground motion. And it's also analogous to what structural engineers use for a pushover analysis. I'm not saying that the soil below the wall or in the wall has 5% damping. I'm using a lumped mass of a certain damping and period on top of the ground or to get the dynamic loading. Because I do not want to use PGA. I want to use spectral acceleration at the degraded period of whatever shaking.
Tú vas a hacer la otra semana.
Mi país, entonces la ayuda incluye y eso no cumplido una buena supervisión como entonces ahora hay una incertidumbre ya que se dice que se diseñó condiciones estables, no condiciones finales. Hay un proyecto SISMIR que realizó los estudios de situación, en el cual se tomaron esos datos y se modeló un análisis 2D y tal, un análisis 2D final, el cual el análisis 2D arrojaba una subida que será un punto estático dio 1.2 y el dinámico dio 0.85. La pregunta es, con todo lo que ¿qué recomendación en este escenario? El incertidumbre en este caso sería hacer una inversión de estudios para el CPU. Lo que se busca es ver la estabilidad, analizando los estudios. Me gustaría ver toda la presentación que dice, cuál sería la metodología de instrumentación y de los estudios, no me recomendaría en este caso, y también el análisis, en este caso sería el análisis 2 de estudio.
That is too challenging for me to answer quickly. I would have to know the geology, the seismology, the ground conditions. You know, in many respects, you found that there were some issues, and I think that the analysis you've done so far, which I don't know the types of analysis and inputs to the analysis, so I can't judge it, there's enough uncertainty there where stepping back and maybe having a group look at this, and having a peer review group look at this to make sure that you do the proper types of field testing and laboratory testing to support the right kind of analysis to help you make that decision would be the way to go forward.
I think the first thing you would want to do, or the first thing I would want to know in reviewing something like this would be the nature of the materials. Are they liquefiable materials? Do they have the potential to lose strength so that you can have tremendous deformation? What would the consequences of the failure be? If the factor of safety is 0.89, depending on the types of materials, that might involve small deformations, or it could involve very, very large deformations if it's a heavily strained, soft, and brittle material. So there are a lot of details that would influence the response there, and they need to be looked at very carefully. It's almost impossible with a brief description like that to come to any conclusions about what should be done. I think the first thing we want to look at is how mobile these materials become and how far they can go.
I have a question about the watering method. I have a question about the watering method, and I know that you don't like it, but I think when a case that you have to excavate the material, and this is a material that is susceptible to destruction, and you have a certified profile of silty sands and silties, the watering method, I don't know if it's recommendable for that case, because I think that it may have less some isolated areas of saturated material. So I want to know what do you recommend to reduce the possibility of destruction when you have this type of profile?
So when you have a silty soil profile,
Yes.
ways to mitigate the liquefaction. I do think you can take advantage of the geology and probably convince yourself with careful sampling that you may not have a problem. If you do have a problem, or if you want to be conservative, then you have to use the CPT results and assume these soils will liquefy. Improving silty soils is challenging because vibratory methods won't work. So you might want to use a displacement type densification, but then you need confinement. Or you can always go to jet grouting or deep soil mixing and solidify a grid system that will then give you rigidity or stiffness so that you won't get high pore pressure generation. Drainage won't work. It's a silt.
One more question.
Yeah.
The last one?
The last. Professor Gray, it's about Quaterem. You just mentioned that there's a newer version of Quaterem. I'm wondering if that version accounts for free boundary conditions, or it's only considering the same compliant base. Because having the boundary condition of the previous version is quite challenging when you have stiffer materials, because you end up with larger models.
Yeah, that's one of the reasons why Flush is a better program to run if you're just looking at dynamic response. But people like Quad 4M because it's been used for dams and it calculates the equivalent acceleration directly. But you do have to have your boundaries far out because it doesn't have the energy transmitting boundaries on the side. The new version, from talking with Marty Hudson, does not fix that problem. When I get the new version from him, he tried to send me an executable copy, but it got eaten up by somebody's filter, spam filters. When I have that, all the documentation, the example problems, I'll give them to you. He's allowed me to share them with everyone freely because it's based on actually something that was supported by the NSF and Berkeley, so it's a free program. Flush allows you to do the calculation, and you can take the mass of each element, the acceleration of each element, and you can calculate the equivalent acceleration for a sliding mass with Flush as well.
Gracias. Hacemos entonces la clausura del evento.
Please, Professor.
Ya le di con agua.